Hi, and welcome to this session about the application of deep reinforcement learning concept to industrial problems. First of all, let me introduce myself. My name is Luigi Manca, I'm from Italy, and I'm a father of two. After achieving the Master of Science in Mechanical Engineer, I co-founded a small management consulting company, focused on relying on simulation modeling techniques to address quantitative solutions to customer strategic problems. A few years later, my company had been acquired by Engineering Ingegneria Informatica Group. From that moment, I'm acting as the Director of Simulation and Digital Twin Practice, especially for the Italian and European markets. Today, I would like to share with you our first experiences about expanding our capabilities of delivering innovative and practical decision support tools for industrial application, leveraging AI and simulation. Before showing the two use cases we prepared, I'd like to drive you through the context and why we think that the deep reinforcement learning coupled with an industrial simulator can be a breakthrough to optimize manufacturing operations. Then, I would like to explain why we believe that this should be within every industrial engineer's reach. Finally, I'll briefly explain two different industrial cases by quickly explaining the background, a few technical details, and the achieved results. Before getting into the problems, I would like to spend a few words about the company I'm representing here today. The engineering group is one of the main players in the digital transformation of public and private companies and organizations, and was established in Italy more than 40 years ago. The group designs, develops, and manages innovative solutions for business areas where digitalization generates major changes, such as digital finance, smart agriculture, and digital industry. It comes on a turnover of more than 1.5 billion euros and approximately 12,000 professionals spread in 40 locations around the world, from Europe to North and South America. Especially Engineering USA is our organization's North American branch, headquartered in downtown Chicago with a team of specialists focused on the technological transformation of the manufacturing and transportation sectors. Also, it's worth mentioning that we have one of the few technological practices focused specifically on simulation and digital twin in the industrial setting. And this is one of our fastest growing areas within our Global Industry Excellence division. Many industrial problems can be described as a series of sequential decisions in which early decisions influence the choices available later on down the line, like a game of chess. We all know that being a manager is all about decision-making. All the decisions can be right or the decision can be wrong, especially when making the right decision now by considering all the possible implications in the future. It's not an easy task. Simulation modeling techniques are extremely useful and can help a lot with this process. They are suitable for an industrial engineer who wants to explore the possible impacts of decision from a systemic perspective, and they allow to explore manually potential optimization strategy. However, when the complexity grows a lot, or when the overall goal is many steps in the future and uncertainty come into play, arriving at the optimal sequential decision without reinforcing the simulation approach with appropriate techniques is nearly impossible. Like I mentioned, many industrial problems can be attributed to sequential decision, where earlier steps influence the choice available later on. In these cases, identifying the optimal things to do is very difficult by simply using traditional techniques. The data gathered for the current state of the systems are used to decide which action is the most suitable to reach our goals. Explicitly or not, we always make decisions to optimize our business objective. Decisions quite always rely on fixed rule or optimizes. Both of these approaches have their advantages, but sometimes express their limitation. For example, heuristics usually don't require a solid mathematical skill to be implemented, and are essentially based on observation. On the contrary, they need a higher priority knowledge of the system to be implemented, and are often biased by stratified human experience. Furthermore, designing the correct action to perform in each state of the system is complicated when high complexity and uncertainty are in the mix. Usually, the result is the fruit of a long and sometimes frustrating manual and error approach that almost always brings a feasible but suboptimal solution. On the other hand, mathematical techniques are mere problem knowledge dependent and are specifically designed to search for a real optimal solution. Unfortunately, many search and plan techniques are not suitable for long-term optimization or can just handle with uncertainty. Sometimes they require expensive online calculation or can't find a solution always. Stochastic programming allows simultaneous optimization of design variables under uncertainty. But also in this case, this is useful only when dimension of the problem is limited. Generally speaking, formalizing a perfect model is really hard. If the model is bad, the optimization will be terrible. So we come to decision agent. It combines mathematical optimization, simulation, and deep learning to train an agent to find a general strategy that can suggest at each step the best action to perform, giving us the highest likelihood to reach our optimal goal. This type of algorithms stand under the name of reinforcement learning. Reinforcement learning is an approach of machine learning, and if I'm not titled to deeply discuss the methods or the math behind it, my goal is to provide you a quick overview of how it works. Reinforcement learning fundamental idea is that we have an environment that represents the system and an agent that take actions. After each action, the agent receives an observation from the environment that consists of a reward for the action and information of the new state of the systems. That reward informs the agent of how good or bad was the action he took, and the recent observation tells him what the effect of his action in the environment was. Iteratively, the agent tries to figure out the best action to take or the optimal way to behave in the environment in order to carry out his task in the best possible way. It basically deals with learning via interaction and feedbacks using trial and error approach. Unlike other machine learning techniques, which essentially are used to group, classify, or predict new data, reinforcement learning aims to find an optimal strategy function to reach a predefined goal whose output varies with the environment. However, classical reinforcement learning algorithms like tabular, SARSA, Q-learning are impractical when the state action space of the problem increases. This is why we leverage the advantages of deep neural net as universal function approximator, which are capable of representing complex nonlinear functions to address complex industrial problems. For sure, this is a fascinating matter because it mimics human learning by experience. And DeepMind proved to the world that deep reinforcement learning could achieve a superhuman level in different tasks. Deep reinforcement learning seems to be a promising and trending technique, at least looking at Google. But why? First of all, it can deliver a policy for sequential decision-making where the environment is nonlinear and complex, or where problems do not have a closed-form analytical representation. In the reinforcement learning settings, no one gives us batches of data for training like it happens in supervised learning. On the contrary, we are gathering data as we go, and the action that we take affects the data that we see. And so sometimes it's worth taking different action to get new data. This is a crucial aspect because it allows deep reinforcement learning to discover optimization policy that sometimes are beyond human intuition. Furthermore, reinforcement learning can deal with the dilemma of exploration-exploitation that involve a fundamental choice. exploration, where we gather more information that might lead to us to better decision in the future, or exploitation, where we make the best decision given the current information that we already have collected. Finally, where the environment is probabilistic, reinforcement learning takes into account the relevant uncertainty and include them into its final trained policy. As said before, in the so-called model-free approach, the agent learns just because of its interaction with the environment. Therefore, a reliable environment is indispensable for training the agent. For business as industrial application, a discrete event or agent-based simulation modeling environment is the best candidate to facilitate the application of reinforcement learning. Essentially because this kind of platform provides a risk-free and low-cost gym for training industrial problems. They are commonly already available and widely used within enterprise, and this means that many building blocks and standard process modeling libraries are already there and ready to be used. Furthermore, when you don't have historical data, industrial simulators allow the modeler to fill the gap of non-complete pre-existing data easily by approximating them with statistical distribution. And another advantage is that having a test bed where the trained policy can be visually checked and stressed after the learning process can create confidence in the users. The black boxed policy seems a little less black. Finally, and this is connected to what I said before about the data, simulation modelings enable the possibility to forecast things that have never happened before and to run scenarios outside of the historical bounds, including crisis scenarios. Despite all these benefits and the intuitive key way of working, deep reinforcement learning hides a bunch of very complex topics that are much closer to a research center than to an industrial customer. I just give you a few examples, but many others could be added to this list. Let's start with the choice of an appropriate reinforcement learning algorithm for your problem. DQN, A3C, proximal policy optimization, multi-agent. There are many algorithms, but there is no best practice yet. A reward function. Shaping a good reward function is at the same time so crucial for the learning process, but so tricky. Decision sequence. Sometimes it's not easy to understand what is the best agent and the best set of action. You can go with a single agent or multi-agent single policy, multi-agent multi-policy. High computational power. Training a deep reinforcement learning agent requires many tentatives, and each one requires time and CPU power. Having access to an inadequate platform lets you save time and money. Observation. Do you want to go with structured or unstructured data? So vector data or image? Correlated feature to reward or not? Formulate your observation in the minimalist way to avoid noise can be really tricky. Seamless integration. The environment and the neural net need to be tightly coupled, integrated, and synchronized. Otherwise, it could affect the training efficacy. Last but not least, hyperparameters. How to fine-tune your artificial neural net. How many layers, how many neurons, which activation function. And the RL algorithm, exploring, forgetting, learning rate. In our opinion, to make deep reinforcement learning suitable to solve practical industrial problems, all these topics need to be transparent to the user. The whole process needs to be as close as possible to the actual way of working of any industrial engineer, and it shouldn't need a PhD grade to be used. As engineering, we are expert in integrating state-of-the-art technologies and proposing robust solutions that can solve real-world problems quickly by avoiding the above-mentioned challenges. For this reason, the two cases I'm going to present in a few minutes have been realized using AnyLogic as the simulation environment and PathMind as the deep reinforcement learning framework and training service. AnyLogic is the leading simulation software for business application. It provides a single platform for all possible business needs in dynamic simulation modeling. Currently, it's the only simulation tools that allow multi-method modeling to simulate business systems of any complexity. And more recently, AnyLogic expanded its functionalities to allow the user to easily integrate and train AI agent using Pathmind or other platform. As discussed before, training an intelligent agent policy using the traditional approach usually involves the needs of building a custom environment with a custom architecture using out-of-the-box Python algorithms, and the entire process is very sensitive to hyperparameter tuning or algorithm choice and neural network architecture. All these points make implementing reinforcement learning a very long, painstaking process. On the contrary, we choose Pathmind because Pathmind tunes hyperparameter automatically, choose the algorithm to fit your problem, and implement state-of-the-art neural networks to keep you focused on modeling the problem and deploying the solution, rather than finicking with the learning knobs. Pathmind on-demand computation allow the user to run dozens of experiments on different models simultaneously, and to seamlessly organize their experiment and their analytics in the cloud, thanks to a rich and easy-to-use web interface. A distinction between Pathmind frameworks and OpenAI Gym, which is essentially single agent, is the ability to control multi-agents from a single control, from individual controllers, or a mix of both. This unique feature gives you the flexibility to apply reinforcement learning to real-world problems. This slide aims to explain how the entire process flow works visually. On the left-hand side, we have the systems we want to optimally control through a deep reinforcement learning approach. The first thing we have to do is to create and validate a working simulation model using AnyLogic. Once we are sure that the model exactly replicated the system behavior, we can then configure directly into AnyLogic all the elements that need to be managed by the Pathmind framework. Essentially, through an object called Pathmind Helper, the user needs to give Pathmind the ability to read the observation space, the metric used to shape the reward function, and to translate the policy outcome in an action that AnyLogic can interpret. As soon as this process is tested, the user exports the simulation model directly into the Pathmind platform for the training. The user then, in the platform, shapes the reward function using the metrics he defined in AnyLogic and launches the training experiment. Pathmind allows running many experiments in parallel to speed up the trial and error approach. Finally, once the policy is successfully trained, the user can import the policy back into AnyLogic to visually validate and ensure that it behaves as expected. Let's now move on the first of the two use cases. The case is related to the optimization of the operation and maintenance of energy system equipped with prognostic and health management capabilities. This problem can be framed as a sequential decision process that deep reinforcement learning can address really well. To demonstrate the proposed approach potentiality, we use a scaled-down case study of a wind farm. The baseline simulation model has been realized by the AnyLogic company and is well known among the users since it's classically used within AnyLogic training courses. The wind farm is composed of 20 identical wind turbines equipped with PHM capabilities. Equipment can fail, and the free maintenance crew, here depicted with this figure of a lorry, are available for the wind farm maintenance. Each maintenance crew can reach a component and perform either preventive maintenance if the component is not broken or failed, or corrective maintenance if there is a problem already. Each maintenance crew can freely move in the 2D scale space, and the crew work on a 24/7 shift. The objective is to develop a deep reinforcement learning policy able to optimally schedule wind turbine maintenance to maximize the wind farm profitability by considering finite maintenance capacity and both failure and production uncertainty. Let's go a little bit into detail. The baseline simulation model, as I said, is a pure agent-based model. Both service crew and wind turbine behavior have been modeled as a finite state machine using AnyLogic UML-based state charts. Equipment exchange messages with the service crew. Each equipment can be in a working state if its own remaining useful life is greater than 0. In this state, the equipment produces energy and revenue. The production profile is affected both by the degradation of the equipment itself and by the wind conditions. Another state of the equipment is a failure state. In this state, its remaining useful life is 0, and the turbine is not producing revenue or energy anymore, and is waiting to be repaired. Once the crew arrives, the equipment moves in the under maintenance state before coming operational again. Service crew instead can be idle if there is no task to perform, otherwise they can be driving in the direction of the equipment to maintain, or they can perform the maintenance, or they can drive him back home. At each moment, Pathmind is able to manage a multi-agent single policy in which each service crew decide if and which equipment serve based on the observation of the status of the equipment, the prediction of the expected production of the next 3 days, the expected remaining useful life, the maintenance cost, and the actual service crew position. The multi-agent policy is also able to coordinate the service crew in order not to assign a single maintenance task to more than one service crew. Here we can see the comparison between a widely used first-in, first-out predictive policy versus the trained deep reinforcement learning multi-agent policy on the right. Both these policies rely on the PHM capabilities, but while the heuristic predictive policy, interventions are performed only if the turbine remaining useful life estimation is smaller than a user-defined threshold, and the service crew serve the equipment based on a first-in, first-out list of order requests, taking into account the time of the threshold exceedance. The deep reinforcement learning is more proactive and can handle multiple objective strategies to maximize the overall profit. Looking at the experiment result on deep reinforcement learning, we can observe a spatial coordination between the agents that can be visually observed, and is demonstrated by looking at the lower average distance per trip covered by each service. Moreover, the deep reinforcement learning performs some over maintenance to cope with the remaining useful life estimation uncertainty, and by avoiding the punishment of having unproductive failed equipment. Overall, all these strategies allow the deep reinforcement learning to overcome the predictive maintenance policy, since the total profit of the deep reinforcement learning solution exceeds the predictive one of more than 30%. We need to highlight that the policy proposed on the left is one of the most studied approach for maintaining energy system, and is not just a Hereford case. Now, let's have a look at the second use case I want to present you today. This particular case concerns the control of a flexible manufacturing system. A flexible manufacturing system is technically and complex and highly automated production line consisting of adjustable machine tools, essentially CNC machines, combined with automatic transport devices, both for the product and the tools. And you can see a couple of pictures of these on the right. The embedded information software collects, processes, and feedbacks various information to implement hierarchical control of the machine tools and of the transportation equipment as well. The objective of the use case is to provide a solution that can avoid bottlenecks and optimize order sequencing to reduce the total manufacturing processing time. Another objective is to move beyond static rules and heuristics with AI-trained agent decision that require no human expertise into the loop. This latest aspect is extremely helpful in reducing the setup phase when installing a new machine, a new line to a customer for which you have no clue. And this allows to increase a little bit the performances since the beginning. As we said, the models aim to optimize the required time to manufacture several orders related to up to 24 different product variants. each job or order needs a fixed number of phases to generate a finished product. Each phase requires a specific machine equipped with a compatible tool and a specific fixture. The association and separation of this tool is performed in the load and unload area. The simulation model has been built as an hybrid discrete event and agent-based approach. The main structure has been realized through the AnyLogic embedded process modeling library, enhanced by the pallet and tool shuttle proactive behavior. Orders arrival depend on a random generation rate. Each product phase needs a specific machine, tool, and fixture type to be completed. The scheduling list is then decomposed into multiple tasks, each of them including the product to transfer, the eventual current holding station, and the task type. It means a load, unload, or the next phase. Station can be booked by task, and then the associated product can be moved with the pallet shuttle. Stations are subjected to failure rates and repair time as well. Each tool can be moved with a tool shuttle through the central tool warehouse for specific phase request or for maintenance. On the deep reinforcement learning side, we choose the pallet shuttle as the single intelligent agent to be trained through PathMind. The agent needs to decide if to insert a new job in the line, the type of the job to insert, and if to reach a station to move a job to the next phase or just to wait. To decide, agent can observe the station utilization and status, the list of waiting orders, the total time passed, tools availability, and which is the next phase for each job currently in the line. The agent then tries to maximize the number of product processing and at the same time to reduce the mean time, takt time of the line. There are also some penalties, like the total time passed or the invalid order insertions that generate blockage. The result shows that the policy found by deep reinforcement learning can balance the number of jobs concurrently on the production line. It can reduce the frequency of production bottlenecks and interruptions. By observing the agent behavior, it brought a heuristic improvement that we then adapted in production. In fact, the original heuristic rule had a fixed constraint of allowing at maximum of 2 concurrent jobs in the line. This constraint was added to the fixed rule in order to avoid deadlocks. By searching for the maximum reward, the agent tried to concurrently process as many jobs as possible. During the exploration phase, the agent was able to successfully manage 3 products at the same time, providing a satisfying line throughput. By mimicking how the agent avoided this deadlock, we consequentially improved the heuristic rule, as said before. Here you can see the finding of 2 scenarios that were creating a blockage in the line. In scenario A, for example, this decision agent efficiently resolved the conflict of 2 products that need a swap of machines for the next phases of their production. In the scenario B, it could also manage the same similar conflict, but with 3 products simultaneously. Another interesting aspect is the strategy used for job insertion in the line. The heuristic rule prioritized the job based on the overall completion percentage. It means that the products near to be completed are the one on top of the list, and consequentially orders are consumed uniformly. Instead, the decision agent is able to find a strategy to consume faster the generated order. It means that it tries to consume first the type of object it prefers. Here you can see the box plot related to the average takt time and the total time passed for both the heuristics and the deep reinforcement learning agent. The plot has been obtained from a Monte Carlo experiment of more than 4,000 runs. In general, the policy reveals to be better than the heuristic one in terms of result. Let's move on to the conclusion. In the presented cases, we limited our scope to train policies on simulated environments, and we use the same policies to improve heuristics already deployed in production. To definitely leverage the deep reinforcement learning approach at its maximum, we need to move forward and directly apply the same policies in the real world. Pathmind is already working on a service that should simplify the deployment in production of the policy, following the vision of allowing the access to these powerful approaches for real industrial application. The policy will be detached by the synthetic data and will be substituted with the data that are directly arrived from the asset, enabling a new kind of real-time prescriptive decision support system. The technology is almost ready, but the changes should be also at the organizational level. At engineering, we are constantly discussing our customer to understand the best and innovative way to do that. A final solution is not here yet, but the future seems promising. Thanks for following this presentation. I hope you enjoyed it. I'm here for the question and answer session if you want, or you can find my contacts on the slides.